Today we're going to talk about multiple comparison procedures. This is going to extend what we talked about with ANOVA. So with ANOVA, we mentioned that the test is omnibus, meaning that it's general. It tells you if there is a difference somewhere, but it doesn't tell you where. This chapter is talking about how to find where those differences are and how to adjust for having a lot of tests that you're running. So as a reminder, the omnibus just means there's some difference. If you have 3 groups, it means there's at least one of the groups is different than the others. It could mean all of them are different. It doesn't really tell us. So it just indicates if one or more significant differences are there among all the possible comparisons. So there's a couple ways we can approach this. There's simple versus complex comparisons. The simple comparisons are really what you're used to with like a t-test. You're comparing 2 of the groups at once. So it's called pairwise. There's a pair. So it's possible for no pair of group means to significantly differ, even when you have a significant ANOVA. When it's right on the edge of 0.05, that happens sometimes. There's also complex comparisons, and this is when you're comparing combinations of 2 or more means. So you actually can combine groups and compare those to other groups. So there's a lot of flexibility in how you actually explore where differences are. So this whole idea, this multiple comparison procedure, it's all about detecting simple or complex differences. Now, one thing to note is that a significant omnibus test is not always necessary, especially when you have some very distinct questions up front, a priori. So sometimes the ANOVA might not be significant, and that could be because our assumptions are violated, or because of type 2 error, which means we just missed it. Because ANOVA has that. Sometimes you're going to miss it with any test. But that doesn't mean that you can't finish testing the questions that you had planned a priori. So it's always okay to conduct multiple comparisons when p-value is close to significance. And particularly when you have research questions a priori that you think certain groups are going to be different from each other. I think this is pretty funny. You'll see this happening out there where someone says jelly beans cause acne. Some scientists look at that. They don't find that. And so they say, well, that settles that. And then someone's like, well, I heard it's just a certain color that causes it. And so they test all of these colors, all the colors. And in all of those, you just find this one. We found a link between green jelly beans and acne. And so what gets printed? Green jelly beans linked to acne. So this is one thing that can happen really quickly when you don't have really good a priori questions. What you can end up doing is exploring all of these things, and then you get something significant, but it's just by chance. And that's because you are testing so many things that what ends up happening is your type 1 error increases. Now, how that happens, this is what this slide is trying to get at. So if you think of your alpha, so generally the 0.05 that we're using, that's your probability of a type 1 error. So if our alpha is 0.05, we're okay with a 5% probability that we'll have a type 1 error. So for each comparison, you have this pairwise comparison alpha, and that's just the alpha rate for any one comparison. So if we run one test and our alpha is 0.05, that is the alpha for that test. We have a 5% chance of committing a type 1 error there. However, we also have this thing we have to consider is the experiment-wise or family-wise, it's another term for it, alpha. And so this is going to be bigger as you have all comparisons. It's going to be bigger than your alpha here. So if you have more than one comparison, it's going to go up. So the equation to actually figure out what your chance of committing a type 1 error is this equation right here. 1 minus, and then in parentheses, 1 minus your alpha level times how many, or to the power of how many comparisons you're doing. So for example, if we're doing one comparison, you can just plug these numbers in and you'll get 0.05 if this is 0.05 right here. But as those comparisons go up, this gets bigger and bigger and bigger. What ends up happening is this is going to get bigger. It's no longer going to just be 0.05, it's going to be larger and larger and larger. And this happens really quickly. So for example, if we had ANOVA with 4 groups and the F statistic is significant, we could just compare each group with one another, which would be all of these comparisons. So that ends up being 6 comparisons with 4 groups. And the pairwise comparison error rate is 0.05. So we actually can calculate what the experiment-wise error rate is. So what we can do is plug in 1 minus 0.05 and then plug in a 6 here. And if you plug all those in, what you end up getting is something around 26%. So even though each comparison is about a 5% error rate, the chance that at least one of our comparisons is committing a type 1 error rate is about 26%. And that's just with 4 groups. So when it goes to 10, so if we had 5 groups, we'd have 10 comparisons and suddenly it's 40%. So really quickly, just with a number of tests, you're going to find that your chance of committing at least one type 1 error is going up really fast. So you have really 3 options of how to deal with this problem. One is ignore one or the other. So you can just say, we're just going to look at our experiment alpha, or we're just going to look at our pairwise comparison alpha. You can modify either one of them. So that's your 3 options. We're going to talk about all 3 during the course of this lecture. All right, so this slide, this is probably going to be one of the more confusing parts of when we're talking about type 1 error. Because what I'm going to tell you is that post hoc comparisons versus pre-planned, or in other words, on this side, ones that you didn't plan in advance versus ones you did, it's going to impact your type 1 error rate, even if you have the same number of comparisons in both. So just to define this side, it's selected after data collection and analysis. It's generally used in exploratory research. And it's a larger set of or all possible comparisons. So you're comparing a bunch of the available comparisons you could do in your study. And what ends up happening is your alpha, so your type 1 error rate for the whole experiment, your whole study, is inflated. On the other hand, if you have pre-planned, these are selected before data collection. They follow hypotheses and theory. Justify conducting any planned comparison. The ANOVA doesn't need to be significant for these. And even though your alpha, your type 1 error rate for the whole study is going to go up, it's not going to go up very much, especially compared to this. And at first glance, you might be like, why on earth would that be? You're still making all the same comparisons. Well, the post hoc ones, those ones you are making decisions based on p-values that you've already seen. So you might have a significant ANOVA that surprises you. And so you're like, I got to find out where the differences are. And so you go in and you start testing. Well, you only started doing those tests because of a p-value. So you already have a chance of being wrong about why you're doing those tests in the first place because of the ANOVA. There's a chance that it's a type 1 error. So by the time you're doing these other tests, you're already at a chance that you were wrong. And so you're building on a more shaky foundation. Where pre-planned is you made these decisions not based on a p-value, you made them based on theory or hypotheses or previous literature. And so they're going to be more grounded in something that's going to have a less likelihood of a type 1 error. So pre-planned is better than post hoc in terms of type 1 error rate. So this kind of repeats a little bit of what I said, but the problem with comparisons for the post hoc or making the decision after the fact is the decision is based on examining the data. And generally, you're only examining the most promising comparisons, which means you're selecting what tests you're going to do based on the results of previous tests. And so you kind of have this inception thing going on where the tests are only happening because of previous tests, which are happening only because of previous tests. And so you have this problem of this inflated type 1 error. In the end, though, when all possible pairwise comparisons are conducted, your type 1 error rate is technically the same, whether it's a priori or post hoc. And that's because either way you arrive at the same destination because you tested all of them. And whether you tested that because you're like, there's some results, let's test them all, or if because that was a previous theory-driven or hypothesis-driven test, in the end, you're going to have the same type 1 error rate if you are making all the comparisons. So to help this make a little bit more sense, consider an example. So assume there's 20 pairwise comparisons that are possible. But in the population, no significant differences actually exist. So we have this godlike power that we know this. But let's say we do the study anyway. We find a significant F statistic. So already we made a type 1 error obtaining a significant F statistic. We shouldn't have concluded that there's an effect, but we did anyway. However, a post hoc comparison using sample data suggests largest and smallest means differ. So we found a significant test, we explored the data a little bit, looking like there might be some stuff. So if we had conducted one planned comparison, then we would have 1 in 20 chance of conducting this comparison and making a type 1 error. In other words, without having made the decision based on seeing the data already, there's only a 1 in 20 chance that we would have found that comparison. But if we had conducted all possible comparisons just to explore it, then there's a 100% chance that we would have done that comparison and made a type 1 error. So even if you don't compare all possible comparisons, but you decide to make only that one comparison based on seeing the data already, then your chance of committing a type 1 error is still 100% because you're going to run that test. Another important concept, so when you have data, you find a significant result, you explore it. Testing the largest versus smallest means is very actually similar to just testing all possible comparisons. It's kind of like a shortcut where you are just taking a side route to get to this instead of doing all possible comparisons, but ultimately the destination is going to be the same. You made a test based on already seeing the data. And a p-value is not designed to give you good information in a situation like that. All right, so with those warnings and cautions, we're going to talk about some ways that you actually can do some tests. Now note, both of these are just names and groups that have been created. You can use any of these techniques in the way that we've talked about with plan comparisons or post hoc, and they're going to act very similar to what we've already talked about. But notably, some of these are going to adjust so that our type 1 error rate isn't as big. Another thing that's important is in most statistical packages, so like SPSS or R, there's really no difference between these. In SPSS, they're all called post hoc, and in R, they're all called multiple comparisons. So the name isn't as important as it is using it based on theory or based on exploration. And before I move on, I just want to say that exploratory research is not a problem. It needs to be done. So doing exploratory research shouldn't be something you back away from. But you need to acknowledge that when you do exploratory research, it's less likely that your results are solid. So when you do exploratory stuff, you need to make sure it's well known that it's exploratory and that there's a chance that your type 1 error rate's high. And with that, you can really benefit the literature by just putting new stuff out there, but making it really clear that it's exploratory. All right, so the first procedure that we're going to talk about is multiple t-tests. So that is literally what it is. You just do multiple t-tests and compare all the comparisons you planned on doing or want to explore. So when you have a homogeneity of variance, you can use this equation. So the MSW straight from the ANOVA output and the means for the groups that you're comparing. If you have heterogeneity of variance and an equal n, you can just use these adjustments. If you have heterogeneity of variance and unequal n, so your groups aren't the same size, you can use this adjustment. But note, it's literally just a t-test. So when you're running this, you can literally just use t.test in R to get this. You also have the Bonferroni Dunn t-test. And this is essentially a t-test, but you're adjusting the cutoff point. So the Bonferroni adjustment is your pairwise comparison rate divided by however many comparisons you're doing. So if we had 6 comparisons and our alpha was 0.05, we would just divide the 0.05 by 6, and this would be our new cutoff. Instead of having each comparison a cutoff at 0.05, it would be at 0.0083. So you'd run all the t-tests just like you normally would, but you'd only say it's significant if it reaches that point. What this does is it keeps your full experiment-wise or family-wise error rate at 0.05. So across all of the comparisons, your error rate is still 5%. But one issue with this is it's more conservative. So you do reduce the type 1 error rate, but that means it's less powerful. It actually, at the same time, increases your type 2 error rate. You're more likely to miss something that is actually there. So the next procedure we're going to talk about is linear contrast. And this is one of those complex ones where you can compare several groups at a time. So literally it's just an equation like this that you build up. And so it's just seeing this for the first time, for me at least, I was like, I don't know what that's talking about. But seeing it in practice actually helps a ton. So consider these examples. So example 1, we have 4 means. And we just want to compare group 1 and group 2 and ignore the others. So what we do is assign a weight to group 1. So we can assign a 1 to them. And then to group 2, we do the opposite, so -1. And then the other 2s we want to ignore, so we can just put zeros. the value you have here isn't so important as that it matches. You have a positive and negative version. So those are the weights we're going to use, and then what you can do is just plug it into the equation. So you can do a 1 in front of the mean of group 1, and a negative 1 in front of the mean of group 2, and then zeros in these ones. And what you end up getting is you're just testing this, the difference between those means. So in this situation, it's literally like doing a t-test. This is not going to be any different than that. But let's say we want to compare group 1, 2, and 3 to number 4. One way we could do this is we could assign a weight of 1/3 to these 3, and then a negative 1 to this one. Or we could do 1s here, and we could do a negative 3 here. Or we could do negative 1/3 for these 3, and then a positive 1 here. What's important is that the comparisons, both sides are going to equal out. So for 1, 2, and 3, if we add all those up, that's just 1. And 4, the one we're comparing to, is also a 1, but in the negative direction. So if we do that, this is the comparison we're essentially getting. Is we're taking the average of these 3 means and comparing it to that mean. So when you're thinking of a linear contrast, it gives you this flexibility to compare multiple means at once, and all it's going to do is just take the mean of those means and compare it to some other mean of means. So you can calculate this by hand, and I'm going to just show you the equations, how to do that. But note that this can be done in R or any statistical package really fairly quickly. These kind of contrasts, they can sometimes be difficult to understand, but they are not difficult for a computer to calculate. So if you have equal ends, this is the equation you get. So the L that we calculated on the other side here. So all of these were the L that we're calculating. So you could just do this by hand right here. And then you plug that in. So n L squared times n for each group, divided by the sum of all the weights that we used squared. So these are just values that we selected or calculated, and we can just plug them in. If you have unequal ends, it changes just slightly where you have to adjust for the ends down here. But ultimately it's the same information. And then that SS contrast ends up getting plugged into the F statistic. So here you have your SS contrast. In this case, it doesn't show it, but just like the other sums of squares that we've used before, you just divide by the degrees of freedom to get this upper one. And so what you end up with is you're basically splitting up your SS between into smaller pieces into these contrasts, and you can compare each one with an F-test. So you just plug in these values, and then you'd have the ratio for the F-test. Now the degrees of freedom for your sums of squares is k minus 1. Your degrees of freedom for the SS contrast is the number of groups or sets included in the contrast minus 1. So in this case, let's go back. So the number of sets here is 2. You have this combination compared to this combination. So in that case, our degrees of freedom would be 2 minus 1, in other words, 1. So going back to the example we had in the last lecture, where we have the mean of no noise group versus the mean of the moderate noise and the loud noise groups, we can compare these. So we could use a -2 to compare the no noise to these two. And what we get is this -5.6 for our L. So our SS contrast is 5, the group size, times the -5.6 squared. divided by all the c's squared. That gives us 26.13. Our degrees of freedom is 2. We have 2 sets that we're comparing to. Minus 1, which is 1. So our MS contrast is this value, minus, or divided by our degrees of freedom, so 26.13. Our degrees of freedom within is just from the ANOVA table. It was 1.9, or 12, and then the MSW is 1.9. So our F statistics 13.75, and our p-value is less than 0.05. So the linear contrast, in a lot of ways, is just like a mini version of the original ANOVA, because you're basically just taking pieces of the original ANOVA and using that to make different comparisons. So as a note, if our alpha is 0.05 and our degrees of freedom for within is 12, our F critical value is 4.75. Thus, it's a significant effect. Now note that our total sums of squares between is equal to the contrast that we could do here. And our first contrast was this one. But what's remaining is we have not looked at the difference between moderate and loud. So we could do that one. So we have a 0 here because we don't want to compare that one. And we have -1 and 1 to compare those two. And we can go through all the same math and get to a pretty small F statistic and a p-value that's greater than 0.05. So the mean of no noise is different than these two, but these two are not different from each other. So when it comes to linear contrast, generally what we're going to be doing is what are called orthogonal tests. And this is what we've been talking about so far. And when we're doing orthogonal contrasts, if M1 is larger than the average of M2 and M3, like we just saw in the previous example, it doesn't tell us anything about M4 and M5. The other option is this dependent or non-orthogonal contrast. We're really not going to use those. They're possible, but they're not incredibly useful. Now, to know that you've done an orthogonal contrast, Rule 1 is saying that the sum of all your weights are 0 for that given contrast. Rule 2 is saying across a contrast, the combination of them, they sum up to 0. So from our example, Rule 1, we have 1 plus 1 plus -2, that's 0. And for the L2, we have 1 plus -1 plus 0, that's 0. So rule 1, check. For rule 2, we're going to combine the two tests. So for L1, the weight was -2. For L2, it was 0 for that specific mean. For the mean of group 2, or the moderate noise, they were a 1 in this one and a 1 in this one. And then for the third mean, it was a 1 in this one and a -1 in this one. And so when you do all that math, it's 0, which means all these contrasts were orthogonal. So that's one of the rules that you want to be making sure that you're careful about when you do any linear contrasts, is that they are orthogonal, because it gives you more interpretable information. I want to just make some recommendations about what to do and when. So if you have one pairwise comparison of interest, just do a t-test. You do not need to make your life harder than it already is. If you have several pairwise comparisons, then you might want to use a Bonferroni version where you're adjusting for the multiple t-tests, but then use Bonferroni, or then just use t-tests. And Bonferroni is the most widely used, but there are other alternatives that we're going to talk about a little bit that are similar. If you have one complex comparison, then just use a linear contrast. You don't have to worry about orthogonal at all, because it's just one. If you have several complex comparisons, then you want them to be orthogonal. And if they are orthogonal, then you don't have to do any formal adjustment. If you're doing non-orthogonal contrast, then you do because of how it works out. So again, if it's simple, do a t-test. If you have several of them, use some adjustment like Bonferroni. If it's a complex comparison, then use a linear contrast. And if you have several complex comparisons, make sure they're orthogonal. All right, the last part of this lecture is all these post hoc procedures. So there's several of them. I'm going to go through them fairly quickly because they work very similarly. They just make different adjustments. So the first one is the Fisher's LSD test. It's also called Fisher's protected t-test. So when you are doing a Fisher's LSD test, you literally are just running multiple t-tests, not making any formal adjustment. The test that's only after a significant F test, that's when you call it a Fisher's LSD test. If it's planned a priori, then you can call it multiple t-tests. And one advantage is that the equal ends are not required, and it's the most liberal post hoc comparison because it's not making any adjustments, so it's really powerful. It can find the effects that actually exist, but it also has a high type 1 error rate. And in general, it's not recommended in most cases. I would only use when k is equal to 3 or less. Another one is a studentized range Q. This one is very similar to a t-test. It makes a few adjustments to it. So this is what it looks like, which looks a lot like a t-test. The reason why this one is used is it uses a slightly different distribution other than the t. And so this is naturally going to adjust for comparing multiple means, but it's still similar to a t in how it works. Of course, there's a table for it. There's always a table for these kind of things, right? So here's the equation again. Again, this Q is coming from a different distribution than a T, and so it's going to be adjusting for things. But note that the studentized range Q assumes all samples are of the same size. So unequal ends can lead to inaccuracies depending on group size differences. So when things get really different, it's going to cause a lot of problems in the distribution itself. So if ends are unequal, you have some alternatives. We're not going to go into any detail here, but there are some. Now note, some of the other ones we're going to talk about today use the same distribution. So this studentized range Q distribution is important. It's much like the T, but it's going to help provide us with ways to compare multiple means, whereas the T is only designed for 2 means. Another one is Tukey's HSD test. This one's really common out there in the wild. It's based on the premise that type 1 error can be controlled for when involving the largest and smallest means. So if you control for that comparison, you're controlling for all other possible comparisons. In other words, if you compare the worst case scenario and make adjustments for that, then the adjustment should work for other cases as well. So a significant ANOVA is not required for you to use a Tukey's HSD test. And again, it's going to be using the Q distribution, the studentized range Q. It's one of the most conservative post hoc comparisons, so it's really good at controlling your experiment-wise type 1 error. So compared to LSD, HSD is less powerful with 3 groups. HSD is more conservative, which means it has less type 1 error. Generally, with 3 groups or more, it's going to be preferred. I personally like using Tukey's HSD in a lot of situations, including when you just have 3. So Fisher's LSD is the most liberal test. Tukey's HSD is nearly the most conservative. The Bonferroni adjustment is the most conservative. It keeps your type 1 error rate exactly 0.05. And then everything else is in between. You can also use the confidence interval HSD. This again is going to rely on the same Q measure. And you're just going to be plugging in these values. So the difference between the means plus or minus Q, your critical Q, times the square root of these values. And so this part is called the HSD. And so if the interval does include 0, you fail to reject the null, and the means are the same, there's no difference. If the interval does not include the null, or 0, I mean, you reject the null, and there's evidence there is a difference. So it's much like the confidence intervals we used with the t-test before, but it's just using a slightly different distribution. Last one I don't recommend. It's a chef's test. It's in the book, so I present it here. We're not going to talk about it much, but it can be used sometimes when you're using really complex contrasts. But overall, you're probably not going to end up using this one a whole lot. So when it comes to recommendations for these procedures we just talked about, if you have one pairwise comparison of interest, again, just use your standard independent samples t-test. If you have several pairwise comparisons, if your group size is 3, then use LSD. If it's greater than 3, then use HSD. Or some of the alternatives such as Tukey's B or Reg WQ. These are ones we didn't talk about today, but they are similar to HSD. There's also Dunnett's test we didn't talk about. As you are starting to see, there's a lot of ways of doing this. In order to not overwhelm and just have too much stuff going on, we've cut it down a lot to just a handful. So just note, when your group size is 3 or less, LSD, which is basically just t-test, is just fine. When there's more than 3, you usually want to use HSD. When you have one complex comparison like a linear contrast, you don't necessarily need to make an adjustment. If you're doing non-orthogonal linear contrast, then Chef's test, that's a one time that you're really going to be using it. But again, I don't recommend this approach. If you're doing orthogonal, use a more conservative cutoff. So like 0.01 could be a good one for a linear contrast. So just to tie everything back together, when we're talking about running an ANOVA, the ANOVA is going to give us some information on whether or not there is a difference somewhere among the groups. What we talked about today are various ways of exploring where those are. So we can have that as a planned, where we are saying these are the tests I'm going to do no matter what. Or it can be, well, if we find a significant ANOVA, then we'll explore and find where the differences are. All of these are going to have costs and benefits to them. For example, the LSD, it is the most powerful, but your type 1 error rate is going to go up. The HSD is less powerful, but it controls your type 1 error rate pretty well. So when you're running your own analyses, it's just good to keep those caveats in mind, and then take a look at the recommendations, as those can be guiding principles for you. Now, the last thing is when the independent variable is really ordinal or really is truly continuous, that's when I would recommend using a linear regression. And everything I have here on the slide is stuff that we cover in the regression class, the 7610 class. We talk about how using a regression, you still get an F statistic, you still get the ANOVA information, but you get even more information with a regression. And in fact, you can even fit curves. So if you don't think that the relationship between two variables is linear, You can even test out curves and see if there's a curved relationship as well. So to finish, not all researchers agree about the best approach or methods here. The method selection depends on a number of things: the researcher preference, the seriousness of making a type 1 versus type 2 error, whether you have equal or unequal ends, if you have homo or heterogeneity of variance. Those are going to impact what you decide. And you also can run mixes of pairwise and complex comparisons. You don't just have to pick one and go with it for the whole study. You have a lot of freedom, and you have a lot of ability to look at what, if you're going for a journal article, what does a journal often use? What do they normally accept? And in my experience, they often accept a lot of these versions. Usually they just want to see that you're taking into consideration what your comparisons are. Last thing to note is anytime that you are adjusting your pairwise comparison rate, so for example, if we lowered it, it would lower our type 1 error probability, but that in turn would increase our type 2 error. So any adjustment you're making to your alpha level is going to impact both error rates. Another thing to note is a priori is more powerful than post hoc. So if you have your planned comparisons to begin with, they're guided by theory or previous hypotheses, you're better off. So generally, a priori is a better choice. So again, exploratory research is important, but it needs to be very clear that it's exploratory. All right, so if you had any questions from this, please post it to the discussion board. We can chat about these. A lot of these you'll end up using fairly naturally when you're doing ANOVA. They're just kind of come with the ANOVA boat when you start using that. Feel free to ask any questions that you have about those.